Nucleavoltaic energy. Okay, more commonly known probably today as nuclear voltaics or nuclear voltaic energy. They kind of still have it separated. In the future, it's all become one word. Voltaic is not even capitalized. That's just what I'm used to. So that I've compromised, and I actually capitalized the V in voltaic, even though it's all one word with just the N capitalized in the future. Nucleavoltaic energy, of course, uses nuclear material for the source of radiation. See, solar radiation and nuclear radiation are both types of radiation. And if you can take one type of radiation and put it up on capture it with voltaics and create energy, then you might be able to use other sources of radiation. Like you might be able to do that. Yeah, sure. Okay. So you get the idea. If you can do it with solar radiation, why not nuclear radiation? Now, there's been some problems, I understand, and from my history, I remember some kind of problems that you guys had with nuclear voltaics in this time period, where the voltaics were not picking up the energy from the nuclear material because the energy was too small. To say the photons are too small for it to capture. It's kind of like a basketball goal, and you know the basketball goes through the basketball goal if it's straight on. But if it's turned to the side and the basketball comes at the basketball goal, boom, and hits it, well, that's what we want. If it doesn't hit it, you think of the basketball hitting the goal as a radiation, a photon hitting a voltaic and being absorbed. So if it doesn't hit, if the ball just goes straight through the hoop and misses, then it doesn't get absorbed by the voltaics. And that's what happens with the radiation from a lot of nuclear materials. Well, you need to explore first of all, other sources of nuclear radiation. And then also there's two methods by which they capture nuclear radiation in the future using voltaics. We have the overlapping voltaics, which is like having two basketball goals, and the ring of one is either under or over the other, and right here where the basketball would try to go through, it's intercepted by the ring of the one that's overlapping. And vice versa, the one over here, this ring right here, as the ball tries to go through this one, well, there's a ring in the way from another basketball goal, and boom, it's captured. Okay, so overlapping voltaics, layers of overlapping voltaics, where the photons the radiation would go straight through. You have layers upon layers, enough layers, excuse me, not like real thick, but so that if it misses one layer of voltaic, the one right underneath it is slightly offset so that they're overlapping and will capture the radiation and absorb and use it. Okay? Then there's angular-oriented voltaics. Okay? Here's a basketball goal. Ball flies straight at it, goes straight through. You know, whoosh, as they say. Well, if you turn it to the side like this, the ball coming at it, boom, hits the ring and is absorbed. So you orient it at a 45 or more degree angle, and they're side by side, so that not to allow, and there's several basketball goals stacked one on top of the other. That's kind of like how the voltaics are designed. Okay, so they're oriented to the side and they're stacked. Okay, so the radiation can't get through. It has to be absorbed by the angular-oriented voltaics that are stacked. They have a stacked design to them. Excuse me. Now, the radiation itself is coming from the nuclear material. We need to talk about the structure or the schematic of the nuclear material. Okay, the problem you guys have today using nuclear energy is the high heat and the possibility of meltdowns. Now, I know you have liquid metal coolants and things like that. Liquid metals work a lot better. You don't even need to watch them a lot of times. The liquid metals will disperse heat well enough that even if your cooling system went down, convection through the liquid metal would actually disperse the heat from nuclear materials well enough that even if the cooling system goes down in those liquid metal cooled nuclear systems. But here's the thing. The reason why you need any of this cooling system to begin with is like coals on a fire. The more coals you have together in one place and they're all hot, the more overall heat you have than if you dispersed those coals out. Same amount of coals, disperse them out so that they can't accumulate their heat together. They can't concentrate their heat together and provide, in the case of nuclear materials, it's too much heat. Okay, and it's too much radiation. But if you have a monatomic schematic for your nuclear material and have each molecule, each atom or molecule or whatever of nuclear material far enough apart that as it's giving off radiation towards the layers of voltaics, you have one layer. This by hand would be like the layer of radiation material. Here would be the voltaics right next to it, okay, like this. And the nuclear materials are spread out in very monatomic schematic all along here. So the radiation is given off to the side. It's given off to this way from the side, and the voltaics pick it up. And the voltaics being either this design, overlapping, or angular orientation. Okay, so that's how it works in the future. You have to do that, and of course, they've got different types of nuclear materials, as you do. You guys already know about this. So find the ones that work best. Use a monatomic schematic. Keep the heat down. Either overlapping voltaics or angular orientation, and you can use nuclear radiation just like you use solar radiation with voltaics, and create a 24/7 source of energy. Okay, so there it is.